So this is part 2, looking at a little bit about the theory about how people are making choices and how we might want to analyze the data once we've got it. So, models of choice. So respondents are being asked to select the best and the worst from a subset of objects. So just in terms of language, I'm going to use the words best and worst, but actual framing depends on context, and there are different forms, most important, least important, so on. But in general, I'll try to stick with the idea of picking best and worst from a set. So what we do in terms of the theory is assume there is some latent, by which I just mean unobserved, measure for each object ui, and that's held within the respondent's mind, and they're using that latent measure of value to respond to the question about which is best and worst. So for the set of objects that they're seeing in the particular set, they pick the one with the highest or lowest utility as the best or worst out of the set. So this is basically a choice process, and if you make some appropriate assumption about the nature of the random element of choice, so you're going to assume, we can't assume that people are completely deterministic utility machines, but there's some element of randomness happening in the way they're making their choices. If we make an appropriate assumption about the distribution of that random element, then we end up with a modern homologic model, as in the standard type of structure of a model. So if you assume there are random elements to choice of a particular form, then it's this logic model. So the probability that they choose item I out of the set is given by the exponential of the beta I, where the beta I is going to be our weight, our utility for that item I, divided by, well, the sum of all of the complete items in the set. And then you can say the same thing about, so this is just, this functional form has nice properties. Probabilities are bounded between 0 and 1. The probability that you choose an item as best, well, they sum up to 1 across the full set. So it has those nice properties. Then what you can think of as being, you can have this, the worsts, as just being the probability that I choose item I as being the worst, denoted by the little tick on the top of the prime, is just the exponential. Well, we just put a minus on the front of these betas, so that just reverses the ordering. I didn't actually include that in here, but so what that's going to indicate is that they are that the probability of choosing something as worst is equivalent of choosing it as best if you just put a negative on all the utilities. So if it had the smallest utility when it was in its default setting, if you multiply everything by -1, then effectively the worst now has the largest utility. And so then this sort of structure, this inverted structure here for the worst, works. And we can basically combine these two things, as in these betas are the same. This is the beta utility that guided us in choosing the best. This is the utility that guides us in choosing this worst, as long as we've got the minus sign on front of it. Okay. There is a particular form of modeling which is known as max diff, and this assumes that what the respondent does when they looked at their choices, that set, they looked at all possible combinations, item 1 and 2, item 1 and 3, item 1, and so on all the way through, and then picked the combination which had the biggest difference between the best and the worst. So if they do that, then that sort of rationalizes why they picked one as being best and one as worst, because that's the combination which gives the largest difference. So this is something which is known as max diff. It's a very specific form of model of choice making, and it's sometimes that name max diff is used to when people are talking about best worst. Strictly that's not true, as in max diff is a term which should be ideally reserved for this particular form of model of decision making. The model looks different. The probability that you choose this combo of I and I prime as being the best is just the exponential of the difference now between utility of the item that was best and the utility that was the item was worst. The difference between that, the gap between them, and then divided by the sum of all possible gaps. So this is just a different way of interpreting the data you've got, and sometimes that's used. And the most important thing here, I think, is to remember that this is MaxDiff is a model of decision making rather than a mechanism for collecting data. The alternative is that you have this idea of sequential best and worst, i.e. that what somebody did was they first picked their best out of them and then they picked the worst. So let's assume that we're just going to start with, simplify this, we're going to talk about best choices only. Then we estimate this logit model here using data from all the individuals. What we're going to do is we're going to code up some data so that there's a dummy variable. The D is a dummy variable. We just take the value of 0 and 1, and it's 1 if that's the object under consideration, 0 otherwise. If you're familiar with any sort of discrete choice experiment, this is just sort of a common way of representing the presence or not of the data. And what we're going to do is that if you were to want to estimate this for the worst choices, well, what does that mean? Well, you just code up your data, but instead of these dummy variables appearing as D's, they appear as with a -1. So that has the property of flipping the ordering, because we're interested in worst, not best. But you can see that these betas now are basically the same between the two models. We have a set of betas, let's hop back. A set of betas applied to a dummy variable. These are the weights we're interested in. In the worsts, well, here's a set of the weights we're interested in, and they're applied to not the presence absence of the dummy, but just -1 times the presence or absence of the dummy variable, of this particular item in the choice set. So what that means is that we can very easily move between best and worst choices. We can use the same parameterization. We just need to be careful how we're coding up the data. And I'm going to show an example of actually what the data looks like in a minute. If you want to use best and worst in the same frame, you just stack the data together. So you're going to have all of the best data, and then, say, to start with, and then underneath that all of the worst choices, the worst data frame, and you can just estimate it as a single model. And then we're getting the power of doing the best and worst because we're estimating the same parameter betas from their choices they made as best and the choices they made as worst. And that's the advantage of this best-worst process, is its power of being able to combine both of those into the same model. So there's a question: should the item selected as best be included in the set for worst? Now, some computer software and designs are set up so that actually once you've chosen the item as best, which you have to do first, you're then re-shown the set but with that item deleted. That makes it absolutely clear that what you're getting is you're making the choice of best first, and then you're making a choice of worst out of the subset. So if you're absolutely sure that they're being forced to make that choice, then you can drop out. The second set of choices comes from a smaller set. Drop if you're sure about the order of choice. Some actually use complete sets for both, as in basically saying we are not clear as to whether or not they were forced to see best and worst, and therefore, although formally they can't have chosen both, as in we cannot impose the ordering on. And actually Sawtooth does that. So this is just an example of what the data set would look like. If you imagine this would be sitting in an Excel spreadsheet, as to how the data is prepared before going into analysis. So this is one where there are 9 objects that we want to do the analysis on. this is the data set actually just for one person, so that's the ID here. And this is giving some information about the sets. So this is set 1 that we're going to be considering. This is set 2, this is set 3, this is set 4. And what you're going to see is that this element here actually all came from the first choice that they saw. The first 3 observations are actually the best data, and the second block is the worst. So you can see there's a little bit of coding going on here. Was it a best? Yes, it's coded as a 1. Was it a worst choice? It's coded as a -1. And what you can see is they've actually dropped the item that was selected as best is not included in the set that was worst. So this is why we've got 3 observations here, then 2 here. Okay, what's this? This is just like an alternative number, 1, 2, and 3. Here is the object. Object 2 was present in option 1, object 4 in option 2, option 8, object 8 in option 3. So the first 3 lines represent the first initial choice. And what you can see here is that how the dummy variables work. Okay, so this is object 2. It has a 1 there. It was present. All the rest of these dummy variables are 0. Here's 4 present. Here is 8 present. So we've got 2, 4, and 8. Where is object 1? We always have to drop one of the objects, and that acts as a base, as in the case with any sort of dummy coding. And then what we can see here is that the choice they made was, well, in this example, they chose object 2 as their best. So that first part of the data represents our the setup for choosing one object out of 3 as best. And then we come to the second block here, which is the worst component. And what you can see is that because we had option 1 was chosen as best, option 2 has disappeared, option 1 has disappeared, and all we have is 2 and 3 left. So we have 2 and 3, this is 4 and 8 are left in, and then we look at the presence or absence. We can see that, well, here's object 4, but now coded as a -1 because this is now the worst choice, and here is -8 because this is the worst choice. And here you can see that, well, when they were asked to make their selection of what was worse, they chose object 8, and there's the one, the choice. So you can see that these first 5 lines of data essentially represent the 2 choices, best and worst. The first 3 represent the coding for how we identify what was chosen as best. This sort of 0-1 indication which option was selected. The set of dummies indicate which object was present in that option, and the fact that they're positive here means this is the best choice. And then we have the subset of the 2 items, which one was chosen as essentially worst, and here we just have the recoding of the -1s. And then we just repeat. So here is the second choice set. The first 3 lines are again the best, options 1, 2, and 3, and this time the objects were 1, 4, and 5. Because it was object 1, none of these dummy variables are coded for anything, they're all absent. Here is object 4 again, coded as 1. Here is object 5, coded as 1. We chose option 2 as being best. And then we see this next one, and we're left with 1 and 3, objects 1 and 5, object 1 not present, object 5 coded as a -1 because this is worst, and they chose object 5 as the worst. So you can see this is quite a simple, straightforward setup of being able to represent all the context of the choices, and we're doing this idea of stacking the data sets together. The bests are sitting here in the first 3, and then the worsts are turning up in the next 2. Then we have the bests and then the worsts underneath. And the differentiation about whether or not it's a best or a worst is just through the way that we code these absence presence of the object in the option. It's a 1 if it was there when we're considering a best, and it's coded to -1. So it just basically going to flip the utility to reflect the fact that now we're choosing the worst, not the best. So that's the basic structure. If you decided not to drop the one which is chosen as best, then we get the full set of values turning up in here. It wouldn't be 3 and 2, it would be 3 and 3. But that's the choice. So that's the way the data looks. Okay, because of singularity, as I said, need to drop one item from the model. It becomes the base. In that example we saw, where they're dropping object 1. It doesn't matter which one is dropped, because we're just interested in relativity between objects. So if we base it on object 1 or object 9, the relativities will stay the same. It just depends on which one we've chosen to have a utility of 0. That's arbitrary. And those parameter estimates are now going to give the preference ratings for the objects. We can estimate those betas. They're going to be common across the best and the worst, and they're going to tell us how somebody rates the objects that we're interested in. A note on coding: dummy coding or effects coding. Dummy coding takes a value of 1 if present set, 0 not. Parameters are estimated relative to the base. In our little example there, it's going to be object 1 is the base. Effects coding: the dummy variable takes a value of 1 if present in the set, 0 if not, and -1 if not and the base case is present. So what that means is that this is the standard effects coding setup. Parameters are estimated relative to the mean of all parameters. So my base now is the average marginal utility, the average score for an object, and then all the other ones are rated relative to the average. Has no impact on the explanatory power of the model, just interpretation. The model fit, everything else is exactly the same, and there's a paper by Delitar which go through and show that, although there's some papers that say there's differences between dummy and effect coding. Not true, as in you can use either one and you can retrieve the parameters from either one. If you give me an effects coding model, I can tell you what the parameter estimates would be coming out of a dummy coding model. You can just move directly from one to the other. So here's a quick example of that, just showing how this works. This is me doing a quick estimation, some data we've got. This is using the dummy coding. This is the fixed effects model, log likelihood. This is our parameters, and 10 has been dropped as the baseline. Here we come doing some effects coding, so you can see that there's the E is turning up here because these are dummies defined with an effects coding. The important thing is, notice the log likelihood is exactly the same. Didn't change my fit at all. And if you put them side by side, the difference between D1 and D2, as in the relative value of D1 relative to D2, 56367, right? If we look at the effects coding, numerically the values are different, and you may think, oh, you've estimated a different model here, it matters, but it doesn't. Look at the difference. If you take the difference between D1 and D2 in the effects coding, it's the same number. So you have no extra information, or no difference in the interpretation of the information about the relative rankings, whether I'm using a dummy coding or an effects coding model. You get the same value. You can retrieve the value of the base if you want to, as in this version. As in the dummy coding, we knew that the value of the base was going to be 0. In this one, you can retrieve it because you just know that it is going to be the negative sum of all the other coefficients, because it's the fact that there are deviations around the mean. So I can pull back what the missing coefficient is, 0.08. So you can get all your parameters back whichever way you go. Okay, so that's using a statistical model. That's saying we're going to, assuming say that you're familiar with the idea of choice models and how to think about estimating statistically when people make choices from many options. But it turns out that you could just use counts, and actually Louvre et al. Suggests, well, you should just start and possibly finish with the count process. What do we mean by doing counts? Well, what they suggest is just for each item, work out the number of times it was chosen as best out of the set minus the number of times it was chosen as worst, and divide it by the number of times it turned up in the design. Now, this is just a little normalization. That nx may be the same for everybody. If you've got a balanced design and everybody's seen the same objects, have seen the same design, sometimes this nx might be different if you've blocked the design or whatever, but this just formalizes the NBW. So it's just the normalized best minus worst. NBW, this is going to be cool. And you can show that this is linear, has this measure. I can just do this for every one of the objects. For objects 1 to 10, how many times was it chosen as best? How many times was it chosen as worst? Divide by the total number of times it was seen. I'm going to get that score is going to give me a relative weighting if I do that across all of them. And it's shown that that is going to be linear with the parameter sets. We're going to show an example of that. There are more complicated versions. This is something called the analytical best worst, so not NBW but the ABW. What's this? Well, it's basically that same idea of best minus worst normalized, but then it's 1 plus that divided by 1 minus that expression, take the log of it all. And there's a paper by Marley which suggests that this might be a better measure, but actually it's depending on the structure of the data, it actually gives you very similar scores. So let's just show a little example of that. This is one of the paper and the data that we had from the ACR project, and there's a paper being written around that, reporting the results. So this was our description. We had 8 objects, a relatively small set to actually have in a design, but here are our 8 objects we wanted people to rank. Experts were going to rank these. They were split up into blocks of 4 out of the 8. They were asked to choose the most and least effective. And so it was being described to them as to what the objects were, and with some little icons in there as well. So we get a nice big data set. We go and do the conditional logic results. We had it from multiple jurisdictions. These are the results for Nepal, and you can see that here we're getting estimates for 7 of the parameters. There's one being dropped, so it's the base. So these are all relative to the base. Easy access to inputs was seen as being the most important, and then all the relativities relative around that. Relatively small sample, we only had 37. This was an expert sample, so it wasn't like a large population, but still we can get significant coefficient. Yes, here, as in the reference item is the easier access to modern technology. So that's the one which got a base of 0, and that's going to be rated second in the list. That's going to have a 0. Easier access to farm inputs is higher, so that's the most important. And then these others are going to be ranked in order. So we could do that statistically. That's the statistical approach. Or we could do the accounts analysis. So this was the number of times, as in the n, number of times it was seen as the same, because this was a balanced design and everybody did all the questions. This is for the items. Each item was seen 148 times. This is the number of times it was best and worst. This is the normalized best worst. This is the analytical best worst. So we're getting a set of relativities turning up in here. And you can see that these were some are positive, some are negative, but the only thing we're really interested in is the relative values down these columns, one for the other. And then the interesting thing is to do a little plot. So what's on the horizontal axis is the parameter estimate for the item from the estimation, the conditional loaded. And then here are on the vertical axis, there are the scores for the normalized and the analytical best worst, the count measures. And obviously there's no absolute relationship between them because they're different mechanisms and they're generating in different ways and the different normalizations. But what you can see, there's a near perfect linear relationship between them. So these are just sitting pretty much not on a perfect straight line. You can see there's some deviations on this one, also on a near perfect straight line. See some slight deviations off the line, but it's very close. those count measures are almost a sufficient statistic for being able to identify or to be able to reproduce the relative rankings of from the statistical model. So this is why Louvier and others suggest, well, actually the counts gets you an awful long way, almost, you could almost say entirely the way, to being able to answer the question, what are the preferences coming out of this data? You don't need to do any statistical analysis. You could just, as long as you've got all data in an Excel sheet and you can count differences between best and worst, you can retrieve a set of relative values, numerical values for the preferences associated with these objects just by counting. And you can also see that because these are sitting on straight lines, well, if I were to do a scatter of the NBW against the ABW, they're also sitting on a line. They're not the same numbers, but they are basically pretty much perfectly collinear. So one-to-one matching. So which approach would recommend you use? Well, the counts is simple. It can be used with individual data, so you can compare across individuals. So in that sense, it looks a good thing. Why do the econometric approach? Well, you can use it to do formal testing of differences across samples. So in our case, we had 3 jurisdictions we were interested in. We can actually formally test now in the statistical model whether the ratings are different across those 3 different groups. So we can just do a normal formal statistical test of equivalence of parameters. So in that sense, going down the econometric routes gives you more power in terms of being able to do that sort of differentiation across if you've got different samples. Given I've got a statistical model, I can now start introducing, say, interactions. So we could have, in this case, it may not work so well with the experts, but if you're doing a population of a broader population, so does age systematically change their preferences, or for years of experience? That could be used for the experts, as in, do the preferences change across time as people get more experience? Well, it'd be difficult to do that using the counts data, but I can just introduce that statistically into the model. So in that sense, it gives me a lot of flexibility to investigate these other determinants of choices. The issue with the econometrics data is that if you want to do individuals and you want to do individual preferences, it runs into problems if choices are what we'd call deterministic. So if somebody is systematically perfectly rating, say always picking an object as best and never as worst and so on, then statistically that causes problems. So that's the only downside of using the econometrics. If you want to use individual level models, it can run into, or models at the individual level, then it can run into problems. But if you're interested in sample averages, or sample averages allowing for some sort of limited interactions with social demographic to get some sort of individual heterogeneity, then the econometrics is probably the better way to go. So that's a good point to stop before we go on and look at interpretation and presentation of the results.